It was 1994. A physics conference was underway at the University of California, Santa Barbara. The air was thick with complex ideas. Stephen Hawking had presented a problem years earlier in 1976. It was a paradox about black holes. According to his calculations, when a black hole evaporates, all the information about what fell into it is destroyed forever. This violated a fundamental principle of quantum mechanics. The principle says information can't just vanish. For nearly 2 decades, physicists were stuck. The two pillars of modern physics, general relativity and quantum mechanics, were in direct conflict. Then Leonard Susskind stood up. He was a string theorist from Stanford. He wasn't on the official schedule to speak about this, but he had an idea. It was radical. He proposed something called the holographic principle. He suggested that all the information about the three-dimensional stuff that falls into a black hole isn't lost. It's not even inside the black hole in the way we'd think. Instead, it gets encoded on the two-dimensional surface of the black hole's event horizon. The information is smeared out, like a hologram. The 3D reality we see could be a projection of information stored on a distant 2D surface. The idea was shocking. It sounded like science fiction. Gerard Hooft, another brilliant physicist, had proposed similar concepts, but Susskind pushed it forward as a direct answer to Hawking. Hawking disagreed strongly at first. He and others thought the idea was nonsense. The debate would rage for years, but that moment in 1994 was a crack in the foundation of how we see the universe. It suggested that space itself and the distances across it might not be what they seem. It made us question the very fabric of reality, from the smallest possible scale to the largest cosmic voids. Number 23. Your car's odometer can't grasp the moon. The average distance to the moon is 384,400 kilometers. A new car has an odometer that reads 0. An average person drives about 20,000 kilometers a year. It would take over 19 years of driving to rack up enough mileage to equal 1 trip to the moon. The total distance driven by all of humanity in a single year is roughly 10 trillion kilometers. That's enough for about 13 million round trips to the moon, but the moon's distance isn't static. Its orbit is an ellipse, not a perfect circle. At its closest point, called perigee, the moon is 363,104 kilometers away. At its furthest, apogee, it's 405,696 kilometers away. This difference of over 42,000 kilometers is why a supermoon looks noticeably larger in the sky. It's simply closer to us. Here's something less known. The moon is moving away from us. Every year it drifts about 3.8 centimeters further out. This is due to the tidal interaction between the Earth and Moon. The Earth's rotation is slowing down, losing angular momentum. That momentum is transferred to the Moon, pushing it into a higher orbit. The process is incredibly slow, but over millions of years it adds up. When the dinosaurs lived, the Moon was closer and appeared larger in the sky. A day on Earth was also shorter. Billions of years ago, a day was perhaps only 18 hours long. We know this distance with incredible precision because of mirrors left on the moon by the Apollo astronauts. The Apollo 11, 14, and 15 missions, along with the Soviet Lunokhod rovers, deployed retroreflector arrays. Scientists on Earth can fire powerful laser beams at these mirrors. The light travels to the moon, bounces off the mirrors, and returns to a telescope on Earth. By timing this round trip, which takes about 2.5 seconds, they can calculate the distance to within a few millimeters. This lunar laser ranging experiment has been running for over 50 years. It has provided crucial data that confirms Einstein's theory of general relativity and helps us understand the complex gravitational dance of our solar system. There's enough space between the Earth and the moon to fit, every other planet in our solar system. If you take the diameters of Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune and add them all up, the total is about 380,000 kilometers. At its average distance, the moon is just beyond that. It's a surprising amount of empty space. Our closest cosmic neighbor isn't really that close at all. It's a vast empty gulf, and this is just the first step. Number 22, Mars is always a yesterday away. The closest Mars ever gets to Earth is about 54.6 million kilometers. This doesn't happen often. The last time was in 2003, the closest approach in nearly 60,000 years. More typically, a close approach puts it around 56 to 60 million kilometers away. The furthest it can be is when it's on the opposite side of the sun from us. Then the distance is a staggering 401 million kilometers. This huge variation is because both Earth and Mars have elliptical orbits and they travel at different speeds. Earth completes an orbit in 365 days. Mars takes 687 days. This distance creates a fundamental problem for communication. The radio waves travel at the speed of light. When Mars is at its closest, a signal takes about 3 minutes to travel from Earth to Mars. So a round-trip message, like sending a command to a rover and getting a confirmation, takes 6 minutes. When Mars is at its furthest, a one-way signal takes over 22 minutes. A round trip is 44 minutes. This time lag makes real-time control of anything on Mars impossible. You can't use a joystick to drive the Perseverance rover. Mission controllers at NASA's Jet Propulsion Laboratory have to plan every sequence of moves carefully. They bundle a day's worth of commands and send them to the rover. The rover executes these commands on its own. Hours later, the scientists get the data back showing what happened. It's like working with a colleague through very slow email. You send instructions and hope they were understood correctly. You won't know if the rover is about to drive off a cliff until many minutes after it has already happened. This is why the rovers are equipped with advanced autonomous navigation systems. They have to be smart enough to avoid obstacles on their own. Getting to Mars is also a long journey. The NASA Perseverance rover, launched in July 2020, took about 7 months to travel the 472 million kilometers of its transfer orbit. It couldn't just point at Mars and go. It had to be launched into an orbit around the sun that would intercept Mars's orbit months later. This is called a Hohmann transfer orbit. It's the most fuel-efficient way to travel between planets. These launch windows, when the planets are properly aligned, only open up for a few weeks every 26 months. If you miss the window, you have to wait over 2 years for the next one. The sheer distance dictates the entire rhythm of Mars exploration. It's not a weekend trip, it's a multi-year commitment, all dictated by the unchangeable geometry of the solar system. Number 21. The sun's light is ancient history. The distance to the sun is the basis for our entire cosmic measuring stick. It's called an astronomical unit, or AU. 1 AU is about 150 million kilometers. Light traveling at 300,000 kilometers per second takes about 8 minutes and 20 seconds to cross this distance. This means we never see the sun as it is right now. We always see it as it was over 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know about it for 8 minutes and 20 seconds. We'd still see it shining in the sky, then suddenly darkness, and the gravitational effect would also take 8 minutes and 20 seconds to propagate, so Earth would continue orbiting the empty space for that time before flying off into the void. But that 8-minute travel time is just the final leg of a much, much longer journey. The light itself is ancient. The photons of light that hit your face today were created deep inside the sun's core through nuclear fusion. The core is incredibly dense. A newly created photon can't just fly straight out. It immediately collides with an atom, gets absorbed, and is re-emitted in a random direction. It takes another step, collides again, and is re-emitted again. It's a process called a random walk. The photon staggers around inside the sun like a drunkard. The journey from the core to the surface of the sun can take anywhere from 10,000 to 170,000 years. Some estimates put it even higher, closer to 1 million years. So the sunlight that warms your skin today began its existence as energy when Neanderthals still walked the earth. It has been trapped inside the sun for all of human history, only to complete its journey in the last 8 minutes. This distance also makes studying the sun a challenge. We can't send a probe into it, but we have sent probes close. The Parker Solar Probe, launched in 2018, is on a mission to touch the sun. It has made the closest ever approach, flying through the sun's outer atmosphere, the corona. In 2021, it flew within 7.8 million kilometers of the sun's surface. At that distance, the heat shield on the probe reached temperatures of nearly 1,400 degrees Celsius. The probe itself is the fastest object ever built by humans. It uses Venus's gravity to slingshot itself closer to the sun, reaching speeds of over 690,000 kilometers per hour. Even at that incredible speed, a hypothetical journey from Earth to the sun would still take about 9 days. Number 20, Voyager 1 is in a place we can barely fathom. Voyager 1 was launched on September 5th, 1977. Its mission was to study Jupiter and Saturn. It completed that mission beautifully, then it just kept going. As of late 2023, it is over 24 billion kilometers from Earth. That's about 162 astronomical units. It is the most distant human-made object. This distance is so great that our usual units of measurement start to feel inadequate. A radio signal, traveling at the speed of light, takes more than 22 hours to reach Voyager 1. A round trip for communication, sending a command and receiving a confirmation, takes nearly 2 days. The team at NASA's Deep Space Network has to be incredibly patient. The signal they receive back from Voyager is also incredibly faint. The spacecraft's transmitter has the power of about 23 watts, the same as a refrigerator light bulb. By the time that signal travels 24 billion kilometers, it is attenuated to a whisper. The power received by the large radio dishes on Earth is about 1/billionth of 1/trillionth of a watt. Voyager 1 is traveling at about 61,000 kilometers per hour relative to the sun, but even at that speed, space is overwhelmingly vast. In August 2012, Voyager 1 crossed the heliopause. This is the boundary where the sun's solar wind, a stream of charged particles, is no longer strong enough to push back the interstellar wind from the rest of the galaxy. It had entered interstellar space. It is the first object from Earth to do so. It is now in a region of space we have never directly sampled before. It is floating in the medium between the stars, but it is still, in a sense, within our solar system. It has not yet left the Oort cloud. The Oort cloud is a theoretical, immense sphere of icy bodies that surrounds our solar system. It is thought to begin at about 2,000 to 5,000 AU and extend out to 50,000 or even 100,000 AU. Voyager 1 will not enter the inner edge of the Oort cloud for another 300 years. It will take an estimated 30,000 years for it to pass through the Oort cloud and truly leave our solar system's gravitational influence behind. The power for Voyager 1 comes from a radioisotope thermoelectric generator, or RTG. It uses the heat from the decay of plutonium-238 to generate electricity. This power source is slowly decaying. By around 2025, it will likely no longer have enough power to run any of its scientific instruments. After that, it will go silent. It will continue its journey through the Milky Way, a silent ambassador from a world it left long ago. It carries a golden record, a gold-plated copper disc with sounds and images selected to portray the diversity of life and culture on Earth. It will not come close to another star for about 40,000 years. The distance it has traveled is a monument to human ingenuity, but it's also a humbling lesson in the scale of our own cosmic backyard. Number 19, Proxima Centauri is our unreachable next-door neighbor. Proxima Centauri is the closest star to our sun. It is 4.24 light-years away. A light-year is the distance light travels in 1 year. That's about 9.46 trillion kilometers, so Proxima Centauri is about 40 trillion kilometers away. This number is hard to comprehend. Let's try to put it in perspective. If we were to use the fastest spacecraft ever built, the Parker Solar Probe, and point it directly at Proxima Centauri, the journey would take about 6,300 years. If you tried to drive there at a constant 100 kilometers per hour, it would take you 45 million years. Proxima Centauri is part of a triple star system, along with Alpha Centauri A and Alpha Centauri B, but it's a bit of an outcast. A and B are two Sun-like stars orbiting each other closely. Proxima Centauri orbits this pair at a great distance, about 1.9 trillion kilometers away. It takes over 500,000 years to complete one orbit. The star itself is very different from our Sun. It's a red dwarf, it's much smaller, cooler, and dimmer. It has only about 12% of the Sun's mass and 0.17% of its luminosity. If it replaced our Sun, it would appear as a dull red ember in the sky, and Earth would be a frozen ice ball. Because it's so dim, it wasn't discovered until 1915 by the Scottish astronomer Robert Innes. You can't see it with the naked eye. The most exciting thing about Proxima Centauri is that it has planets. In 2016, astronomers confirmed the existence of Proxima Centauri b. It's a rocky planet, slightly more massive than Earth, orbiting within the star's habitable zone. The habitable zone is the region where temperatures could be right for liquid water to exist on the surface. This was a monumental discovery. The closest star to us has an Earth-sized planet in the right place for life. But there's a huge problem. Proxima Centauri is a flare star. This means it has frequent, violent outbursts of radiation. These flares can increase the star's brightness dramatically in just a few minutes. A large flare would blast any nearby planets with X-rays and charged particles. A 2017 flare was so powerful it would have delivered a radiation dose 4,000 times greater than what Earth experiences from a solar flare. This would likely strip away the planet's atmosphere and sterilize its surface. So while Proxima b is our closest exoplanet, it may not be a very hospitable place. The vast distance means we can't go to check. We can only study it from afar, piecing together clues from the faint light that took 4.24 years to reach us. Number 18, the Pleiades cluster is a nearby cosmic nursery. The Pleiades, also known as the Seven Sisters or M45, is an open star cluster in the constellation of Taurus. To the naked eye, it looks like a tiny, fuzzy patch of light, like a miniature Big Dipper. Most people can see 6 or 7 stars, but through a telescope it resolves into a breathtaking collection of hundreds of stars. The cluster is about 444 light-years away from us. This means the light we see from these stars tonight left them around the year 1579, when Sir Francis Drake claimed California for England. A message sent from Earth today at the speed of light would not arrive until the year 2467. The stars in the Pleiades are young, hot, and blue. They formed together from the same giant cloud of gas and dust about 100 million years ago. This is very young for stars. Our sun is 4.6 billion years old. The dinosaurs were already extinct when the Pleiades stars were born. A distinctive feature of the cluster is the faint blue nebulosity that surrounds the brightest stars. For a long time, it was thought that this was the leftover material from the star's formation. But more recent studies have shown this is not the case. The cluster is simply passing through an unrelated cloud of interstellar dust. The dust is scattering the blue light from the hot stars, creating what's called a reflection nebula. It's a cosmic coincidence that creates a beautiful visual effect. The cluster contains over 1,000 confirmed stars, but it is dominated by a handful of bright ones. The 9 brightest stars are named after the 7 sisters of Greek mythology, and their parents Alcyone, Atlas, Electra, Maia, Merope, Taygete, Pleione, Seleno, and Asterope. The stars are gravitationally bound, but not forever. Over the next 250 million years, the cluster will slowly drift apart as it orbits the center of the Milky Way. Its stars will disperse and become individual members of our galaxy's stellar population. We are lucky to live at a time when This beautiful cluster is still intact and relatively close for us to see. Its distance is great enough to be unreachable, but close enough to be one of the most stunning sights in the night sky. Number 17, Betelgeuse's fate is already decided. We're just waiting for the news. Betelgeuse is a red supergiant star in the constellation of Orion. It's one of the brightest stars in the night sky, easily recognizable by its distinct orange-red color. It marks the left shoulder of the hunter, Orion. The distance to Betelgeuse is not precisely known, but current estimates place it at about 550 light-years away. This means the light we see from it left around the year 1473. When Christopher Columbus set sail, the light from Betelgeuse that would reach our eyes today had already been traveling for 19 years. Betelgeuse is a colossal star. If you placed it at the center of our solar system, its surface would extend past the orbit of Mars and possibly even Jupiter. It is nearing the end of its life. It has run out of hydrogen fuel in its core, and has swelled up to this enormous size. Sometime in the next 100,000 years, it is expected to explode in a supernova. It could happen tomorrow, or it could happen in 90,000 years. We don't know for sure. What we do know is that because of the 550 light-year distance, the event may have already happened. Betelgeuse could have exploded in the year 1800, and we still wouldn't know. The light from that explosion is still on its way, racing toward us through space. We are watching a ghost, a star whose fate may have been sealed centuries ago. When it does explode, it will be a spectacular event for us on Earth. The supernova will be as bright as the half moon. It will be visible during the daytime for weeks, maybe even months. It will be the brightest supernova ever recorded in human history. After it fades, the familiar shape of Orion will be changed forever. One of its main stars will be gone, replaced by a beautiful, expanding cloud of gas called a supernova remnant. In late 2019 and early 2020, Betelgeuse underwent a strange and dramatic dimming event. It faded to about 40% of its usual brightness. This led to a lot of speculation that it was about to explode. However, further study by the Hubble Space Telescope revealed the cause. The star had ejected a huge cloud of hot gas. This gas then cooled and condensed into dust, which blocked some of the star's light from our point of view. The Great Dimming was a stellar burp, not a death rattle. But it was a powerful reminder that we are watching this giant star from an immense distance, seeing its ancient light and waiting for news that is already old. Number 16, the Orion Nebula is a window into our own past. The Orion Nebula, also known as M42, is a diffuse nebula situated in the Milky Way, just south of Orion's belt. It's the middle star in Orion's sword. To the naked eye, it looks like a fuzzy star. With a simple pair of binoculars, it becomes a glowing cloud. A telescope reveals it to be a vast, turbulent region of gas and dust where new stars are being born. The nebula is about 1,344 light-years away from Earth. This is a significant jump in scale. The light we see tonight from the Orion Nebula left during the time of the late Roman Empire around the year 679 AD. It has been traveling through space for the entire history of the Viking Age, the Renaissance, and the modern era. The nebula is a stellar nursery. It is the closest region of massive star formation to Earth. The entire complex is about 24 light-years across and contains the mass of 2,000 suns. Deep inside the nebula is a very young, open cluster of stars known as the trapezium. These are the stars that make the nebula glow. They are hot, young, massive stars that are blasting out intense ultraviolet radiation. This radiation is ionizing the surrounding hydrogen gas, causing it to fluoresce, much like a neon sign. What we are seeing in the Orion Nebula is a process very similar to what happened in our own cosmic neighborhood 4.6 billion years ago. Our sun and its planets formed from a collapsing cloud of gas and dust, just like the ones we see in Orion. So looking at the Orion Nebula is like looking at a picture of our own solar system's babyhood. The distance of 1,344 light-years makes it a perfect laboratory for studying star formation. It's far enough that we see a large active region all at once, but it's close enough that telescopes like Hubble and the James Webb Space Telescope can peer deep inside and see individual protoplanetary disks around newborn stars. These are the disks of dust and gas where planets are currently forming. So when we look at Orion, we are seeing the birth of new solar systems, a process that happened here long ago. The light from those infant systems will not reach us for another 1,344 years. Number 15, the Kepler Space Telescope showed us a galaxy full of worlds. NASA's Kepler Space Telescope was launched in 2009. Its mission was to find Earth-sized planets orbiting other stars. It did this by staring at a single patch of sky for 4 years. The patch of sky it monitored was in the constellation Cygnus. It was a region far from the plane of the Milky Way, chosen so that the view would be filled with a dense field of distant stars. The stars in Kepler's field of view were, on average, between 600 and 3,000 light-years away. This was a deliberate choice. Kepler was not looking for our nearest neighbors, it was conducting a statistical survey. It needed to look at a huge number of stars at once to figure out what fraction of them had planets. The telescope monitored the brightness of about 150,000 stars simultaneously. It was looking for tiny periodic dips in a star's brightness. These dips could be caused by a planet passing in front of the star, an event called a transit. The distances involved are immense. A star that is 3,000 light-years away is so far that its light began its journey to us around 1000 BC. That was the time of the Late Bronze Age in the Mediterranean. Civilizations rose and fell on Earth while that light was in transit. Kepler was incredibly successful. It discovered thousands of confirmed exoplanets and thousands more candidates. The data from Kepler completely changed our understanding of planets in the galaxy. Before Kepler, we only knew of a handful of exoplanets. After Kepler, we know that planets are everywhere. The data suggests that there are more planets than stars in the Milky Way. On average, every star has at least one planet. Kepler found rocky worlds, gas giants, super-Earths, and mini-Neptunes. It found planets orbiting in the habitable zones of their stars. One of the most famous discoveries was Kepler 186f, a planet about 500 light-years away. It was the first rocky planet found in the habitable zone of another star. The legacy of Kepler is that it took the question, are there other Earths, and gave us a statistical answer, almost certainly yes. There are likely billions of Earth-sized planets in the habitable zones of Sun, like stars in our galaxy alone. These worlds are scattered across vast distances, separated by hundreds or thousands of light-years. They are too far to visit, too far to communicate with, but Kepler showed us they are there. It turned our galaxy from a collection of lonely stars into a tapestry of countless possible worlds. Number 14, Sagittarius A, is the monster in the middle of our room. At the center of our Milky Way galaxy lies a supermassive black hole. It is called Sagittarius A, pronounced Sagittarius a star. It is a gravitational monster. It has a mass of about 4.3 million times the mass of our Sun. All of that mass is compressed into a region smaller than the orbit of Mercury. Sagittarius A is located about 26,670 light-years from Earth. When the light we see from the region around the black hole began its journey, modern humans were just beginning to paint in the caves of Lascaux in France. The entire history of agriculture, civilization, and recorded history has taken place during the time that light has been traveling to us. We can't see the black hole itself, of course. Its gravity is so strong that nothing, not even light, can escape. But we can see its effects on the things around it. For decades, astronomers have tracked the orbits of stars very close to the galactic center. And one star, called S2, orbits the black hole once every 16 years. Its orbit is highly elliptical. At its closest approach, it gets to within 17 light hours of the black hole and travels at about 3% the speed of light. By tracking these orbits, astronomers can use Kepler's laws of planetary motion to calculate the mass of the object they are orbiting. This is how we know the mass of Sagittarius A with such precision. These observations provided the first conclusive evidence for a supermassive black hole at the center of our galaxy. And in 2019, the Event Horizon Telescope project captured the first ever image of a black hole's shadow. That first image was of the black hole at the center of the M87 galaxy. In 2022, they released the image of Sagittarius A. The image shows a dark central region, the black hole's shadow, surrounded by a bright ring of glowing gas that is being warped and bent by the black hole's immense gravity. Getting this image was a monumental achievement. It required a network of radio telescopes all over the world, working together to create a virtual telescope the size of the Earth. The data they collected was so massive it had to be flown on hard drives to a central processing center. The distance to our own galactic center is so vast that it takes this level of global coordination just to get a blurry picture of the monster that lurks there. We live in a calm suburban spiral arm of the Milky Way, but at its downtown core, 26,670 light-years away, is a region of extreme gravity and violence that governs the entire galaxy's structure. Number 13, the far side of the Milky Way is functionally another universe. Our Milky Way galaxy is a barred spiral galaxy. It's a giant spinning disk of stars, gas, and dust. Our solar system is located in a minor spiral arm called the Orion Arm, about 2/3 of the way out from the center. The diameter of the Milky Way's disk is about 100,000 light-years. Some studies suggest it might be even larger, perhaps up to 200,000 light-years across if you include a sparse outer ring of stars. Let's stick with the more conservative 100,000 light-year figure. This distance is, for all practical purposes, infinite. If you could travel at the speed of light, it would take you 100,000 years to cross from one side of our galaxy to the other. To put that in perspective, modern humans have existed for about 300,000 years, so a journey across our own galaxy at light speed would take 1/3 of our species' entire history. This means we will never leave our galaxy. Barring some physics-defying breakthrough like warp drive, humanity is confined not just to our solar system, but to our little corner of the Milky Way. The vastness of our own galaxy also limits our communication. We have been broadcasting radio signals into space for about 100 years. Those first signals have now traveled 100 light-years in every direction. This creates a radio bubble 200 light-years in diameter around the Earth. Inside this bubble are thousands of stars. But this bubble is a tiny, insignificant speck compared to the whole galaxy. Our presence has reached only 0.2% of the way across the galactic disk. 99.8% of the stars in the Milky Way have no idea we are here. They are too far away. If a civilization exists on the far side of the galaxy, say 80,000 light-years away, and they sent us a message today, it would not arrive until the year 82,023 AD. If we replied immediately, our message would get back to them in the year 162,023 AD. A single exchange of hello would take 160,000 years. Meaningful conversation is impossible. For us, the other side of our own galaxy is as remote and unreachable as another universe. We share a single gravitational structure, but we are separated by an unbridgeable gulf of time and space. Number 12. The Large Magellanic Cloud is a ghost we once touched. The Large Magellanic Cloud, or LMC, is a satellite galaxy of the Milky Way. It's an irregular dwarf galaxy that, along with its smaller sibling, the Small Magellanic Cloud, can be seen from the southern hemisphere. They look like two faint, detached pieces of the Milky Way. The LMC is about 163,000 light-years away. This is the first distance on our list that is entirely outside our own galaxy. The light from the LMC that we see tonight left during the Pleistocene epoch, long before the dawn of human civilization. Early humans were living in Africa, but they were not yet us. The LMC is in a chaotic orbit around the Milky Way. It is rich in gas and dust, and is undergoing vigorous star formation. It contains about 10 billion stars, roughly 1/100th the number in the Milky Way. One of its most famous features is the Tarantula Nebula, a massive star-forming region that is far more active than anything in our own galaxy. If the Tarantula Nebula were as close to us as the Orion Nebula, it would cast shadows on Earth at night. In 1987, the LMC became host to the first supernova visible to the naked eye since 1604. It was called supernova 1987A because the LMC's distance is well known. The supernova became an incredibly important event for astronomers. It allowed them to test their theories of stellar collapse and supernova explosions with unprecedented detail. For months, it was a major news story. But the event we were watching in 1987 actually happened 163,000 years ago. We were watching an ancient cosmic ghost explode. Recent studies of the LMC's motion using data from the Hubble Space Telescope and the Gaia satellite have led to a surprising conclusion. The LMC is probably not in a stable orbit around the Milky Way. It is likely on its first and only pass. It's a newcomer to our neighborhood. It's moving too fast to be captured by the Milky Way's gravity. It will swing by and then continue on its journey into the void. However, there is another, more dramatic theory. The LMC is more massive than previously thought. This mass is causing it to lose energy and drag against the Milky Way's halo. Instead of escaping, it might be on a collision course. In this scenario, the LMC will merge with the Milky Way in about 2.4 billion years. This will be a major event, triggering a burst of star formation and potentially reigniting our dormant central black hole. So this nearby galaxy, a constant companion in the southern sky, is either a fleeting visitor or our eventual doom. Number 11, the Andromeda Galaxy is our future wreckage. The Andromeda Galaxy, also known as M31, is the closest major spiral galaxy to the Milky Way. It is the most distant object you can see with the naked eye under a dark sky. It appears as a small, faint, fuzzy patch. Andromeda is 2.537 million light-years away. This is a leap to an entirely different scale. The light you see from Andromeda when you look up at the sky tonight left that galaxy 2.5 million years ago. At that time, on Earth, the genus Homo had just evolved. Our distant ancestors, like Homo habilis, were walking the plains of Africa. The light from Andromeda has been traveling for the entire span of human evolution. Andromeda is a beast. It's bigger and more massive than the Milky Way. It contains about 1 trillion stars compared to our galaxy's 100 to 400 billion. Its disk is about 220,000 light-years across. It's the dominant member of our local group of galaxies. We know its distance with great precision thanks to a type of star called a Cepheid variable. These stars pulsate, and their pulsation period is directly related to their intrinsic brightness. By measuring the period, astronomers can determine how bright the star truly is. By comparing that to how bright it appears, they can calculate the distance. It was Edwin Hubble's observations of Cepheid variables in Andromeda in 1923 that proved it was a separate galaxy, an island universe, and not a nebula within our own Milky Way. This discovery fundamentally changed our understanding of the universe. It was suddenly a much, much larger place. The most mind-bending fact about Andromeda is that it is coming right for us. By measuring the blue shift of its light, astronomers have determined that it is hurtling toward the Milky Way at a speed of about 110 kilometers per second. There is no doubt. The two galaxies are on a collision course. The collision, dubbed Milkomeda, is predicted to happen in about 4.5 billion years. It won't be a solid crash. The space between stars is so vast that individual stars will likely not collide. Instead, the two galaxies will pass through each other. Their Immense gravity will distort and stretch them, throwing off long tails of stars and gas. They will then pull back together and merge over hundreds of millions of years. The result will be a new giant elliptical galaxy. Our solar system will likely survive, but our night sky will be forever changed. For a time, it will be filled with the spectacular sight of a galaxy merger up close. The distance between us and Andromeda is not just a space, it is a closing gap, a countdown timer to a cosmic cataclysm. Number 10, the local group is our tiny galactic suburb. Our Milky Way and the Andromeda Galaxy are the two largest members of a collection of galaxies called the local group. This group is a small gravitationally bound cluster of over 80 galaxies. The vast majority of these are small dwarf galaxies, many of them satellites of either the Milky Way or Andromeda. The local group occupies a volume of space about 10 million light-years in diameter. It's a sphere with Andromeda and the Milky Way near the center, orbiting a common barycenter. The third largest member is the Triangulum Galaxy M33, which is about 3 million light-years from us. It may be a satellite of Andromeda. 10 million light-years is a space so large that light takes 10 million years to cross it. A radio signal sent from a civilization on the far side of the local group would be traveling for longer than humans have existed as a distinct species from chimpanzees. The local group is our galactic neighborhood, but it's an incredibly sparse neighborhood. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 7.5 meters away. The Triangulum Galaxy would be a salad plate a bit further out. All the other dwarf galaxies would be the size of coins and crumbs scattered around the room. The space in between is almost entirely empty. Our understanding of the local group is still evolving. Thanks to deep sky surveys, new faint dwarf galaxies are still being discovered. These ultra-faint dwarfs are some of the oldest, most dark matter-dominated, and least evolved galaxies known. They are like fossils from the early universe. The local group is not static. It is moving through space. The entire group is being pulled by the gravity of larger structures. It is traveling at about 600 kilometers per second relative to the cosmic microwave background radiation. This motion is a clue to the distribution of mass on even larger scales. Our entire cosmic suburb is on a journey, falling towards something much, much bigger. Number 9, the Virgo supercluster is a city we live in, but cannot see. Our local group is not an isolated island. It is part of a much larger structure called the Virgo supercluster. A supercluster is a massive collection of galaxy groups and clusters. The Virgo supercluster is a flattened, filamentary structure containing at least 100 galaxy groups and clusters. It is about 110 million light-years in diameter. The light from the far side of our own supercluster has been traveling since the time of the dinosaurs. The Cretaceous-Paleogene extinction event, which wiped them out 66 million years ago, happened while that light was only halfway through its journey to us. The heart of the supercluster is the Virgo cluster, a massive cluster of about 1,300 to 2,000 galaxies, located about 54 million light-years away in the direction of the constellation Virgo. This cluster is so massive that its gravity dominates our region of the universe. The local group, our home, is on the outskirts of the Virgo supercluster, and we are falling toward its center. The Virgo cluster is pulling us and all the other galaxies in the supercluster toward it. This motion is called the Virgo infall. The total mass of the Virgo supercluster is estimated to be about 1 quadrillion solar masses. That's a 1 followed by 15 zeros. It contains roughly 30,000 galaxies, but even this immense structure is mostly empty space. If you were to travel through it, you would spend almost all of your time in the vast, dark voids between the galaxies. The supercluster is not a solid object. It is a lacy, web-like distribution of matter, a filament in the even larger cosmic web. And we live inside this structure, but we can't see it directly. We can only map it out by painstakingly measuring the distances and positions of thousands of galaxies in all directions. It's like trying to understand the shape of a forest while being tied to a single tree. Number 8, Laniakea is the invisible continent our galaxy calls home. For a long time, the Virgo supercluster was thought to be the dominant structure in our part of the universe. But in 2014, a team of astronomers led by Brent Tully redefined our cosmic address. They developed a new way to define superclusters based on the gravitational flow of galaxies. They mapped the motions of over 8,000 galaxies in our vicinity. They found that the Virgo supercluster is just one lobe of a much, much larger structure. They named this new supercluster Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is 520 million light-years across. It contains about 100,000 galaxies, including our own Milky Way. Its total mass is about 100 quadrillion solar masses. This structure is so vast that light takes over 500 million years to cross it. The light from the far side of Laniakea started its journey before the first complex life emerged on land on Earth during the Cambrian explosion. The team defined the boundary of Laniakea as the point where the gravitational flow of galaxies diverges. Inside the boundary, everything is flowing inward toward a central point. Outside, galaxies are flowing away. The central gravitational point in Laniakea is a region called the Great Attractor. This is a massive concentration of mass located about 150 to 250 million light-years away. For decades, astronomers knew something huge was out there because it was pulling our local group and other nearby clusters toward it. But it lies in the zone of avoidance, a part of the sky obscured by the dust and stars of our own Milky Way, making it very difficult to see. Laniakea is our home supercluster, our cosmic continent. The Virgo supercluster is just a province within it. But even Laniakea is not a permanent structure. The expansion of the universe, driven by dark energy, is working against the gravity that holds Laniakea together. The structure is being stretched and pulled apart. Unlike a galaxy cluster, it is not gravitationally bound. Eventually, the galaxies on its outer edges will be pulled away by cosmic expansion. We live inside this celestial continent, but it is slowly dissolving into the cosmic ocean. Number 7, the Sloan Great Wall, was a record-breaking cosmic behemoth. As we look at the universe on even larger scales, we find structures that challenge our models of cosmology. One of the first of these was the Sloan Great Wall, discovered in 2003 from the data of the Sloan Digital Sky Survey. It was, at the time, the largest known structure in the universe. The Sloan Great Wall is a galactic filament, a vast, elongated superstructure of galaxies. It is located about 1 billion light-years from Earth. Its most striking feature is its length. It measures 1.37 billion light-years long. A billion light-years is a distance that is truly beyond human experience. The light we see from this structure left it when the first multicellular life was just beginning to form on Earth. The planet was a simple world of algae and bacteria. All of geology, evolution, and biology as we know it happened while that light was traveling toward us. To travel 1.37 billion light-years, even at the speed of light, would take 1.37 billion years. That's about a tenth of the age of the universe. The structure itself is not a solid wall. It is a web of superclusters and voids. It contains several massive superclusters, including one known as SCL 126, which is the densest region within the wall. The existence of a structure this large was a problem for cosmologists. According to the cosmological principle, the universe should be roughly homogeneous and isotropic on very large scales. That means it should look about the same everywhere, with no preferred direction. As a structure that is 1.37 billion light-years long seemed to violate this principle. It was just too big to have formed in the time since the Big Bang, according to some models. Subsequent analysis has led to some debate about whether the Sloan Great Wall is a single gravitationally bound structure or a chance alignment of smaller, unrelated filaments. Regardless, its discovery showed us that the cosmic web, the large-scale structure of the universe, is lumpier and more complex than we had imagined. It's a universe of immense filaments and even more immense voids that separate them. Number 6, the Hercules Corona Borealis Great Wall shouldn't exist. If the Sloan Great Wall was a problem, the Hercules Corona Borealis Great Wall is a full-blown crisis for some cosmological models. Discovered in 2013, it is the largest known structure in the observable universe. It is a galactic filament located about 10 billion light-years away. Its size is what makes it so baffling. It is estimated to be about 10 billion light-years long. This is nearly 10% of the diameter of the entire observable universe. The light from this structure has been traveling for 10 billion years. It left when the universe was only 3.8 billion years old. Our own solar system had not yet formed. The universe was a much younger, more turbulent place. The existence of the Hercules Corona Borealis Great Wall is a major theoretical puzzle. The cosmological principle suggests that there is a theoretical upper limit to the size of cosmic structures, often estimated to be around 1.2 billion light-years. A structure that is 10 billion light-years across is simply too big. There has not been enough time since the Big Bang for gravity to assemble something so vast. It would require matter to have moved faster than the speed of light to get to where it is today. The discovery was made by mapping the locations of gamma-ray burst GRBs. GRBs are incredibly powerful explosions that occur when massive stars die or when neutron stars merge. They are so bright they can be seen from across the universe. By looking at the distribution of GRBs on the sky, astronomers noticed a significant clustering in the direction of the constellations Hercules and Corona Borealis. This clustering suggested the presence of a huge concentration of galaxies, a Great Wall. The discovery is still controversial. Some scientists argue that the data is not statistically significant and that the wall could be a random illusion. But if it is real, it means there is something fundamental about the large-scale structure of the universe that we do not understand. It points to a profound gap in our knowledge. It is a structure so distant and so large that it seems to defy the known rules of cosmic evolution. Number 5, Jade's GS Z13-0 is a faint glimmer from the dawn of time. In late 2022, the James Webb Space Telescope JUICE made a groundbreaking discovery. It identified a galaxy called Jade's GS Z13-0. This is currently one of the most distant and earliest galaxies ever observed. Its distance is often stated in terms of its redshift, a measure of how much its light has been stretched by the expansion of the universe. Its redshift is Z equals 13.2. This corresponds to a light travel distance of about 13.6 billion light-years. This means the light from this galaxy that the JUICE captured has been traveling for 13.6 billion years. The universe is only about 13.8 billion years old. So we are seeing this galaxy as it was just 320 million years after the Big Bang. The universe was in its infancy. It was a period known as the Cosmic Dawn, when the very first stars and galaxies were just beginning to form and light up the darkness. This galaxy is not a grand spiral like our own. It is a small, clumpy, irregular collection of young, hot stars. It is a baby galaxy, one of the building blocks of the larger galaxies that would come later. Discovering galaxies like this is one of the primary missions of the JUICE. It was built to see the first light of the universe. The distance to these objects is so extreme that it's more useful to think about it as time. We are not looking across space, we are looking back in time. Seeing Jade's GS Z13-0 is like a historian finding a single, blurry photograph from the first minute of a new civilization. It gives us a glimpse into a time we could only previously theorize about. These early galaxies seem to have formed faster and earlier than many models predicted. They are brighter and more numerous than expected. The juice is forcing astronomers to rethink their models of early galaxy formation. Each new most distant galaxy discovered is not just a record breaker, it's a new piece of the puzzle of our own cosmic origins. Number 4, the cosmic microwave background is a wall at the end of time. There is a limit to how far back in time we can see with telescopes. No matter how powerful the telescope, we cannot see the Big Bang itself. This is because for the first 380,000 years of its existence, the universe was a hot, dense, opaque fog. It was a plasma of protons, electrons, and photons. The photons, the particles of light, were constantly scattering off the free electrons. They couldn't travel more than a short distance before being deflected. The universe was like a thick cloud. Then, about 380,000 years after the Big Bang, the universe had cooled down enough for protons and electrons to combine and form the first neutral hydrogen atoms. This event is called recombination. Suddenly, the photons were free. They could now travel unimpeded through space. The cosmic microwave background, or CMB, is the light from that moment. It is the afterglow of the Big Bang. It is the oldest light in the universe. It comes to us from every direction in the sky. It is a surface of last scattering, a wall in time beyond which we cannot see. The CMB was discovered by accident in 1965 by Arno Penzias and Robert Wilson, two radio astronomers who were trying to eliminate a persistent background noise in their antenna. That noise turned out to be the most important discovery in modern cosmology. The light from the CMB has been traveling for about 13.8 billion years to reach us. When it was emitted, the universe was hot, about 3,000 Kelvin. The light was in the visible and infrared spectrum. But over the last 13.8 billion years, the expansion of the universe has stretched the wavelength of this light. It has been redshifted all the way down to the microwave portion of the spectrum. The temperature of the CMB today is a frigid 2.725 Kelvin, just a few degrees above absolute zero. The CMB is incredibly uniform, but it has tiny temperature fluctuations on the order of 1 part in 100,000. These tiny ripples are the seeds of all future structure. The slightly denser, cooler spots were the places where gravity would later pull matter together to form the first stars, galaxies, and clusters. Our entire existence can be traced back to these minuscule fluctuations in a 13.8 billion year old wall of light. Number 3, the edge of the observable universe is further away than its age. The universe is 13.8 billion years old. This might lead you to think that the observable universe is a sphere with a radius of 13.8 billion light years. But that is incorrect. The actual radius of the observable universe is about 46.5 billion light years. This means its diameter is about 93 billion light years. How can a distance be larger than the age of the universe in light years? The answer is the expansion of space itself. Consider a galaxy that emitted the light we are seeing today very early in the universe's history. Let's say it was 13.6 billion years ago, like the galaxy Jade's GS-Z13-0. When that galaxy emitted the light, it was much closer to us. But in the 13.6 billion years that the light has been traveling toward us, the space between us and that galaxy has been expanding. The galaxy has been carried away from us by this expansion. It's like two people walking toward each other on a rubber sheet that is being stretched. Even though they are walking, the distance between them can still increase. The galaxy that emitted the light we see as the cosmic microwave background was only about 42 million light years away from us when the light was emitted. But during the 13.8 billion years the light traveled, that galaxy has been carried away to its current distance of about 46.5 billion light years. This 93 billion light-year sphere is our observable universe. It is everything whose light has had time to reach us since the beginning of the universe. It is our cosmic horizon. Anything beyond this horizon is for now unseeable. Its light has not had enough time to reach us yet. Every year, the cosmic horizon expands by 1 light-year, but due to the accelerating expansion of the universe driven by dark energy, there are galaxies beyond the horizon that we will never see. They are receding from us faster than the speed of light. This is not a violation of relativity because it is space itself that is expanding. The galaxies are not moving through space faster than light. They are being carried along by the expansion of space. Our observable universe is a finite bubble in what might be an infinite sea. Number 2, the universe beyond our horizon is the realm of pure conjecture. The observable universe, with its 93 billion light-year diameter, is everything we can possibly see. But there is no reason to think that the universe ends at our horizon. Our horizon is a limit of our sight, not a physical edge of reality. The universe beyond what we can see could be vastly larger. How much larger? We don't know. According to the theory of cosmic inflation, the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. If inflation is correct, the entire universe is at least 10 raised to the power of 23 times larger than our observable universe. This number is a 1 followed by 23 zeros. It is a number so large that it is meaningless. It means the nearest edge of the universe, if one even exists, is so far away that we could never reach it or see it. For all practical purposes, the universe might as well be infinite. If the universe is infinite and the distribution of matter is roughly uniform, then some startling conclusions follow. An infinite universe must contain an infinite number of galaxies, stars, and planets. And if there is a finite number of ways that particles can be arranged in a finite volume of space, then any given arrangement must repeat itself. This means that somewhere out there in the unobservable universe, there is another Earth with another you reading this exact text. And there are an infinite number of such copies. There are also copies where you made a different decision this morning, and copies where the dinosaurs never went extinct. This is the multiverse concept in its simplest form. It's not about parallel dimensions, but about the inevitable repetition of possibilities in an infinite space. This is, of course, pure speculation. We have no way to test what lies beyond our cosmic horizon. It is a realm of mathematics and philosophy, not observational science. But it is the logical conclusion of our current understanding of cosmology. The vastness of the observable universe is humbling. The potential vastness of the entire universe is a concept that dissolves the mind. Number 1, the smallest possible length puts all cosmic distance in perspective. We have traveled from the moon to the edge of speculation, but to truly feel infinitesimally small, we must look not just out but also in. The largest distances are contrasted by the smallest. In physics, there is a theoretical limit to how small a length can be. It is called the Planck length. It is derived from fundamental constants of nature, the speed of light, the Planck constant, and the gravitational constant. Its value is about 1.6 x 10 raised to the power of 35 meters. That's a decimal point followed by 34 zeros and then a 16. This is the scale at which our current understanding of physics breaks down. The laws of quantum mechanics and general relativity cease to make sense. It is the quantum foam where space-time itself is thought to fluctuate wildly. The Planck length is so small that if you were to scale up an atom to the size of the entire observable universe, the Planck length would be about the height of a single tree. Now consider this. The diameter of the observable universe is about 93 billion light-years, which is roughly 8.8 x 10 raised to the power of 26 meters. The smallest possible length is 1.6 x 10 raised to the power of 35 meters. The ratio between the largest scale we know and the smallest scale we can conceive is about 10 raised to the power of 61. This range of scales is the arena of our reality. Our own human scale, a couple of meters, is almost exactly in the geometric middle of this vast range. We are the fulcrum between the unbelievably large and the impossibly small. The distance to the moon makes you feel small. The distance to Andromeda makes you feel insignificant. The size of the unobservable universe makes you feel like nothing. But the gap between a single meter and the Planck length is just as profound as the gap between that meter and the edge of the universe. The vastness is not just outside of us, it is also inside every atom of our being. The cosmic distances do not just make us feel small, they show us that we are poised on a knife's edge between two different kinds of infinity.